Hi there, welcome to the probability video on Venn diagrams and set language. We will discuss ways to describe parts of Venn diagrams and then show how to analyse relationships among sets within the diagrams. Having looked at the Venn diagram in a previous video and on the website, it is now time to formalise the language we use, to describe relationships in unambiguous ways, and to analyse relationships among two or more sets. To do this, we will use Venn diagrams and extend these ideas by introducing some explicit mathematical concepts and conventions. We will start by taking a Venn diagram as shown here, which represents a situation for a particular group of Year 11 students at a school. Now, 40 students participate in non-school sports, so on the weekends or so. 70 students participate in school sports and 30 students participate in both non-school and school sports. Now there were 30 students who took both school and non-school sports, so we put that 30 in the overlap between the two circles. There were 40 who did non-school sports, but 30 have already been accounted for, so there's 10 who only do non-school sports. Similarly, of the 70 who did school sports, 30 have been accounted for in the overlap, so that what the difference means that there's 40 now who only do school sports. And if we take all of those numbers away from 100, then we find that there's 20 students who do no sport. If we wanted to write these as probabilities, then we simply divide each of these totals above by 100 and get the values that you can see there on the screen. So now we describe the group of students that do either school or non-school sports. There's a combination or a union between the two groups. And so what we do there is to write, instead of A or B, as we did before, we write A, U, B, and the U stands for union. So we say it's the union of sets A and B. So the number who are in the union of it means all of those who do A or all of those who do B, so it's A union B, which is 80 students altogether, because the 80 students did sport. And the probability of that, of course, is 0.8. Rather than talk about students who play any sport, regardless of being non-school or school sports, we may want to focus on just those students who play both forms of sport. So we need to look at the space which is common to both sets, that is, the intersection of the two sets. So rather than write N, bracket, both A and B, as we did before, we can now write N, A, and an upside down U to represent intersection B, and say it's the number in the intersection of sets A and B. Hence, the number in the intersection of A and B is 30, and the probability of picking a student at random in the intersection of the two sets is 0.3. The final piece of nomenclature we need is for when we want to exclude a set. So for example, we might want to exclude all those people who do non-school sports, so set A, from our counting, and just refer to the people who are outside of that group. So we can write to indicate this A dash, or A with a bar on top, or AC. In terms of the Venn diagram above, the number not in A is the part that we've shaded in brown, and it means the number of students not in set A. So the number not in set A is simply 40 with a balance of B, and the 20 who are outside both forms of sport, so 60. Also, if we're looking at the number who are outside B, then we take the balance of those in A, 10, plus the outside group, which is 20. So now we've got our basic nomenclature established, we're able to formalise statements about the two sets. For example, we'll take the number in the union of the areas not in A and not in B. Well, not in A is everything outside of A, which is shaded in brown here. Not in B is everything outside of B. So it's the balance of what's in A and the outside bit of 20. So A not union B not is everything that we've now got shaded. So the number in this region of not A union not B is the total number 100 minus the one on the intersection between the two, which is 30, so the balance is 70. Writing this result in a different way, we can say that the number in the union of not A and not B is equal to the total minus the number in the intersection of A and B, which is the number not in the intersection of A and B, so 100 minus 30. Extending our principle of excluding areas, we can now examine the number in the intersection of not A and not B. Well, again, not in A is everything outside of A, not B is the everything outside of B. So the intersection of those two regions is everything which is common to both shadings, which is simply the area outside the circles. So the number in the intersection of not A and not B is simply 20. Writing this result in a different way, we can say that the number in the intersection of not A and not B is the total minus the number in the union of A and B, which means that we've got the number not in the union of A and B. A very important statement is what we refer to as the addition rule. If we look at the original numbers and ask how many students are involved with sport, we might be tempted to conclude 110 because 40 did non-school sport and 70 did school sport. That ignores the 30 students who do both forms. But we cannot subtract the 30 doing both forms of sport from each of the totals. Hence, our approach is to add the two basic totals together, numbers in each of the circles, and subtract the number doing both forms of sport from that total. So the number doing any sport is calculated as the number in A plus the number in B minus the number in the intersection. Mathematically, we can write the number in A union B is equal to the number in A plus the number in B minus the number in the intersection, which is 80 equals 40 plus 70 minus 30. These totals can be converted into probabilities simply by dividing by 100. So we can see that the probability of something in the union between A and B is equal to the probability of something being in A plus the probability of something being in B minus the probability that something is in the intersection. This statement that we've got here is referred to as the addition rule, and it's very, very commonly used. So we need to generalise the addition rule now to incorporate the various set interrelationships. Given the new diagram at the left, where the total number of students is 50, then the probability of someone being in set A is 0.6, which is 25 plus 5 over 50. Probability of someone being in B is 0.5, which is 5 plus 20 over 50. And the probability of someone in the intersection between the two sets A and B is 0.1, which is 5 over 50. So the probability of the combination of everything in both A and B can be written as the probability of A union B, which is 0.6 plus 0.5 minus 0.1 equals 1. Someone has to be in the shaded area. There is nothing else to count. Extending this to the intersection between them, we could look at the probability of the combination of A and everything outside of B. So we could write the probability of A union everything outside of B, or B dash, is the probability of A plus the probability of B dash minus the probability of the intersection between the two, which gives us 0.6 for the number in A plus 0.5, the number not in B, minus the intersection 0.5, which gives us 0.6. Conversely, we can have the probability of the intersection of B and everything outside of A. So we write that as probability of A dash intersection B, which is the probability of not in A plus the probability of in B minus the probability of the union between those two. So we just swap things around. So that gives us a value of 0.4. Reversing that situation, we can now have a look at the probability of someone in A intersection someone not in B, which is, we can write simply the probability of someone being in A plus the probability of not being in B minus the probability of the intersection between those two. So again, we've got 0.6 plus 0.5 minus the 0.6, because we're looking at something that's common to both regions. So the answer is 0.5. The final combination is the probability of the intersection of everything outside of A and everything outside of B. In other words, there's nothing left from either region. So we just write down our normal statement and we find the probability of being outside the diagram is 0. Finally, we have the situation where the two sets A and B do not overlap at all. So there's nothing in common. Consequently, there's nothing in the intersection between A and B. So therefore, we can extend the addition rule by writing the probability of the union of A and B is simply the probability of being in A plus the probability of being in B. We describe this situation as that the two sets A and B are mutually exclusive, and by that we will always imply that no member of A is also a member of B. Very important. From this same diagram, we can write another result, which is that the probability of something not being in A is equal to 1 minus the probability that it is in A, because we've got this idea of mutual exclusiveness. So the probability of an outcome not being in set A is simply 1 minus the probability that it is in set A. So we can summarise everything that we've said previously in the video, that Venn diagrams can and should be used to analyse relationships between sets of observations, whether you're dealing with just numbers of people or you're dealing with probabilities. There are special conventions used to write the relationships mathematically. We can describe the set of people using a letter instead of a name. We can use the symbol A dash or a variation of that to mean everything outside of a particular set. We can talk about the combination or the union of two sets, so to mean everything in set A and in set B, and use the symbol of a U. Or we can talk about the intersection using the upside down U to indicate everything that is common both to set A and to set B. Then finally, we use those conventions to establish the addition rule, which says that the probability of the union between A and B is equal to the sum of the separate probabilities for A and for B, and minus the probability of the intersection of A and B. And then we use that rule to define the condition for sets A and B to be mutually exclusive by eliminating the intersection term, and so it's the probability of the union is equal to the sum of the two individual probabilities. So that's it for this video. Hope you learnt lots. Click the like button and also subscribe so you can see the other videos that are there now, or the new ones as they are uploaded. Also visit the website drjoesmaths.com to access stacks of tests, information and importantly maths humour.